Welcome to lesson 5.2. Today we're going to review and learn a little bit of new material about rational functions and how to transform them. Starting out, we've got a little math notes box and we'll just take a look at it briefly. Okay, it's just talking about rational functions. It says a rational function is one that can be expressed as a ratio of two polynomials. So there's some examples listed below, and you'll notice each of these is kind of like a power equation. Remember, x has to be raised to a whole number power in each of the expressions, right? So we have x to the second power. On the bottom, we have an x to the first plus 3, right? On the second one, we have negative 2, which is like negative 2 times x to the power 0, right? Which is why we can have a constant term. And on the bottom, x squared minus x plus 1. Okay, so you see it's a quotient. There's just a numerator and denominator, and each of them follow the rules for polynomial functions. Down below, it kind of shows some examples of things that we can't have. Like, for instance, we can't have the square root of x, because that's like x to the 1/2 power. We can't use the absolute value of x. And then this one is not written as a quotient, right? Remember, because we see that addition. However, there are some rational functions that may look similar to that we'll see as we work through the lesson. All right, let's move on. So this one says, write an equation for the graph shown below. All right, so you see that we obviously have a hyperbola, and what they want us to do is to come up with the equation. Before we do that, let's talk about what we know about rational functions. We know that our parent graph for a rational function usually looks something like this, right? So our equation would be like y equals 1 over x, or we've got our y-axis and our x-axis. And then when we think about, like, if we were to make like a little table real quick on the side, they're just thinking about the values. Usually the values we look at, just something like -1, 0, and 1. If we put those into the function, right, this would be saying 1 divided by -1, which gives us -1 as the output. We can't put 0 in there, right, so that's undefined. And then if we put 1 in there, 1 divided by 1 is equal to 1. So we're looking at those points -1, -1. This one would have a vertical asymptote. And then this one here, we would have the point 1, 1. Okay, so when we're drawing our graph, usually we take it here, right? We know we have our vertical asymptote here. And we actually know that we'd have a horizontal asymptote too, right? Because you can't take 1 and divide it by something to get an output of 0. And if we put our point at 1, 1 and our point at -1, -1, this is where our hyperbola shape comes from. So remember, it runs right along the asymptotes, which in this case on our parent graph are just the axes, right? And it goes like this. Okay, so that's our parent graph that we hopefully are familiar with. What they're asking us to do is come up with the equation for the one that is already printed for us. So the first thing, let's just go ahead and draw in the asymptotes, right? You can see there's a vertical asymptote here, and then there is a horizontal asymptote that runs along this direction. And remember, there's a key point here. The locator point is right here where those two asymptotes cross. On our parent graph, right, our locator point was at the point 0, 0, right? It's that place where the two asymptotes cross. Okay, remember this is also considered to be our h and k. So if we were going to write it in its general graphing form, right, we just need to identify what h and k are. So when we look at this one, right, we've got our point, looks like we've gone over 1 to the right, 2 to the right, 3 to the right, and then we've climbed up 1, 2. So this is the point 3, 2, which is like our h and our k. So when we go to write out the equation that we have there, we're just using that form that we've learned in the past. Y is equal to a over x minus h plus k. Right, in this case here, we've identified what h and k are. So as I go to start putting those in here, we're going to say this would be like y is equal to, we have in our denominator x minus our h, so x minus 3. and we'd have our k would be 2, so it'd be plus 2. The only thing we also need to think about here is when we look at our original parent graph, right, it's up kind of, if you're thinking about it, it's in like quadrants 1 and 3. Well, this one looks like it's been flipped, right? It's been flipped. So we also need a negative stretch factor in this one. So this would be like a negative 1 over the quantity of x minus 3 plus 2. And you can put that negative in front of the fraction or up with the 1. It doesn't matter. Okay, now, what they want us to do is to take this, right? And down below, might be a new skill for some of us, or the first time we've done this with rational functions. They want us to write our equation as a rational function in the form that we just looked at in the math notes box, where we've got a polynomial divided by a polynomial. So taking it out of graphing form, okay, and then to like our rational function, or I'll call it the polynomial form, okay? So we're going from graphing form to our polynomial form. So we'll take our function and we'll move it down below. We've got that y is equal to, and I'm going to put my negative in front of the fraction down here. I've got 1 over x minus 3, and then plus 2. Okay, so if we want to take this and write this as a polynomial, and it's that polynomial form, right, what we're going to have to do is combine it into one fraction. So in order to do that, we need a common denominator. And if we look here, right, x minus 3 is the only denominator we can see. So since we know that 2 is just over 1, we're going to give it the same denominator. We're going to multiply the 2 by x minus 3 over x minus 3. So we can get the common denominator. So what we have now is a negative. We've got 1 over x minus 3 plus a 2, and we're going to multiply it times the quantity of x minus 3 over an x minus 3. Now, if I wanted to cancel those, I'd be right back to where I started, right? If I canceled the factors of x minus 3 there, but we're not trying to go that route. We're trying to actually go the other direction. So we're going to take this, and let's combine it into one fraction, right? And I'm going to go ahead and take that negative and just give it to the 1. So I have a negative 1, and then I'm going to be adding to it 2 times the quantity of x minus 3. And now it's all over just an x minus 3. Okay, so I just combined these two fractions, since they have the same denominator, combine them into one. And our last step here is just to go ahead and simplify the top. Right, so we'd have a negative 1 plus, and when we go ahead and distribute this 2 through, right, we'd have 2x minus 6. Right now it's still over the x minus 3, and then when we take it here and finish it, we're just going to combine our like terms, and we get our 2x minus 7 over x minus 3, right? That is what equals y. So if we took that fraction, that function, we'll say, and we took this function, they will give us the exact same graph, right? These are equivalent. That's a great way to check it. Graph them on the calculator and see, do they have the same graph? And they should. All right, so let's move on. This is just some basic stuff here, but if we can make sure we understand these basic skills, this will help us with some of the new skills that we're going to do in the next part of the lesson. Okay, so the first thing they give us is a problem that says write 20/17 as a mixed number. Okay, so we're going way back, right? We're going way back to probably elementary or middle school, but let's just think about it, right? I have 20/17, right? And I'm going to think about how many holes can I pull out of there, right? It takes 17/17 to make a hole. So I could think of this as being like 17 plus 3 over 17. And if we separated those and gave them each their own denominator, right, we'd have 17/17 plus 3/17. which is the same as 1 plus 3/17, or in the end, 1 3/17 is how we would normally read it or write it. Okay, so it's not the, I mean, a lot of us can just look at it and tell me what that answer is, but I want you to think about the process, because the process is a process we're going to use when we go to switch our polynomial form into our graphing form for our rational functions. You'll see that coming up. So here we go. It says, what if you were asked to write 19/4 as a mixed number? Well, same thing, right? We think about it as we've got 19/4. Now, we know that 4/4 makes a whole, so how many wholes would we have there, right? We'd probably have, 4 wholes? We'd have 16 plus 3/4. And that would be like saying 16/4 plus 3/4, or 3 plus 3/4 would be our answer. So 3 and 3/4 is that, I'm sorry, not 3, it's 4, isn't it? My fault. Yeah. Sometimes we say one thing and we mean another. There we go. Should be 4 and 3/4. All right, so let's move on. Okay, so now we're going to apply that same process to our rational functions, right? If I gave you something that looks like this, y is equal to, and we have the quantity of x plus 2 over x plus 1. And I asked you to graph that. We've never graphed that before. So what we're going to look at doing here is we're going to use a very similar process to help us turn this into its graphing form, which should make it easier for us to graph. Let's start out. We're going to take our y equals, and we've got our x plus 2 on the top. What I'm going to do here is I'm going to go ahead and, because this x is really important, I'm going to put parentheses around it. I'm going to call it just x in parentheses plus 2 over x plus 1. Okay, why am I doing that? Well, what I'd like to do is I'd like to try to make this x match this expression down here. So if you think about it there, right, what's missing out of the parentheses? I'm going to need 1, right? So what I'm going to do here is I'm going to take it and I'm going to write x, and I'm going to add 1 in there. Now if I add 1 in there, it's like I'm kind of like I'm pulling 1 from here, right? So if I add 1 in there, I'm going to lose 1 on the outside just to keep it balanced, right? If we look at it here, it's like x plus 1 in the parentheses. Well, now I'd have that plus 2, but I'm going to have to take away 1 from that 2 in order to keep it balanced. If I simplify this top expression, simplify this expression here, I have the same thing still. I've kept it balanced. But if I add 1 inside of here, I got to take away 1 on the outside just to make sure that everything stays balanced. Now, this is still over the same denominator. I haven't done anything with the denominator yet. Hopefully that makes sense. If not, reach out and we can talk about it. Okay, but what's that going to do for me? Well, what I have here now is x plus 1, right? And if I take that 2 and subtract 1 from it, right now it's like plus 1. It's still over an x plus 1, but the reason I did it there is so that I can actually now split it and give each part of the numerator its own denominator. Check it out. We've got x plus 1 over the x plus 1. You don't really need the parentheses. I just listed them in there because I already had them. Then we have plus the 1 also over an x plus 1, right? Give them each their own denominator. And as we go to simplify this, right, can anything reduce down? Right, we've got x plus 1 divided by an x plus 1, which just gives us 1. So that's the equivalent of saying 1 plus 1 over x plus 1. And if you want to flip it around, it might look even more familiar to you, right? We could say this is y equals 1 over x plus 1 plus 1. This is our graphing form. So when we look at our graphing form, right, thinking about what's h and k, So if we're trying to write that out there to move our asymptotes, remember our h is going to be -1, because right, this is like saying x minus a -1, right? So we have -1, and then our k is +1. That is the point where our two asymptotes are going to cross. So let's go ahead and draw those in. At -1, +1, we'll just draw that in. And this one looks like it just has standard growth for a rational function, which means we're just going to use those points that are over 1 and up 1. This would have been like that point 1, 1, and this would have been like that point -1, -1, because there is no stretch. There's nothing happening there with our A. And then we can just sketch in the rest of it. We've got, here it goes, comes down like this, and goes this way. And then we'll do the same thing over here. Run right along our asymptote, hit it, and go down. And if you're not sure if those points are right, just you can always double check. Check us out, right? You've got, this is the point 0, 2. If I plug that into my function, it'd be like saying 2 should equal 1 over 0, my input, plus 1, and then plus another 1. Well, that's 1 over 1 is 1, and 1 plus 1 we know is 2, and that equals our 2. We know it's in the right spot. Okay, that should also work with our original equation. But we've never seen anything like this, or been asked to graph anything like that, so we're going to turn it into the form that we know, which is our graphing form, in order to graph them. All right, let's move on. So, just similar problem here, just giving us a little practice. It says rewrite the function below as a transformation of y equals 1 over x, and then graph. Okay, so we'll work on this one together. So remember, our first step, what we're going to do, we're going to say, hey, we're going to look to start breaking it apart. I've got 3, and I'm going to put that x in parentheses again, minus 7 over x minus 3. So again, remember, we want what's in here to match what's in here. So as we take this and we insert that minus 3 in there, I've got 3 times the quantity of x minus 3. Okay. We got to figure out here, we have that minus 7, but what do we have to do over here to keep it balanced? That's the question, right? We still have this x minus 3 on the bottom as well. Well, by inserting this minus 3 in here, we got to think about, kind of like when you're completing the square, you have to pay attention to really how much are you taking away, right? I am taking away, when I do this, it would have been like 3 times x, it would have been 3x, and then 3 times this negative 3 is really minus 9. So I've really taken away 9. So I'm taking away 9. So how do I balance that out? Well, I'm going to have to add 9 outside, right? If I'm taking away or subtracting 9, then I need to add 9. So I'm going to add 9 on the outside here. So what does that do for us? Well, now we have 3 times the quantity of x minus 3. And then when I do that minus 7 plus 9, that's going to be a plus 2. And then I'm going to take it and I'm going to give both parts its own denominator. I kind of cut over one of the steps that I did in the previous one where I wrote it as one fraction first, but just for space sake so you can follow along, I just went ahead and jumped over that step. So you could write it as one fraction first and then split it if you're more comfortable with that. I just did it in one step. Okay, now, can we reduce either of these? Yes. The whole reason we did this was so we could reduce that out. So what we have here is 3 plus 2 over x minus 3. So when we go to write it, just to make it a little bit more familiar, it looks like our locator point will be at the point 3, 3, and it has a vertical stretch of 2. So just to remember how to do that, right, let's go over here to the graph. I guess I have to go down, you have to go right, but either way. So our locator point, right, our HK, just so we don't have to flip back and forth, was 3, 3, and our stretch factor was 2. So remember that locator point is where the asymptotes cross, so I'm going to put a little little crosshair there, right? There's where our asymptotes cross. And then we could just draw in the rest of it. So if we look at it here, right, we have a horizontal asymptote at y is equal to 3. Remember, that comes from just y equals k, right? So remember, that just comes from y equals k, in case you forgot that. And then we have a vertical asymptote. And that vertical asymptote is at x equals 3. Remember, or x equals h, if you forgot that in the past there. All right, so the other thing here, remember, normally we would take it and we would put in a point, we go over 1 and up 1. We put a point right there, and we go back here and we put a point there. But since this one is being vertically stretched, right, instead of going up 1, we're going to go up 2. So we're going to put a point right up here. So we kind of went over 1, and then we went up 1, 2. Now, this can also go the same way. We can go over 2 and up 1 and get another point. And that just is a unique feature with our rational functions, right? We can go left 1 and down 2, stretch it, but then we can also go left 2 and down 1 there because it's being pulled away from our locator point. And then we'll just draw in our graph. It runs right along there. Okay, so graphing them really shouldn't be a new skill. It's something that we know already, but I know some of us might be a little rusty, so I'm just adding a little extra detail in case you need it. But here we go. We've got, if you're not sure if they're right, again, take a point and plug it in. I'll choose this point here. This is the point 1, 2, right? It's the point 1, 2. I think our function was y is equal to, I'm going to have to peek back real quick. In fact, we can let's just use our original function on this one. 3x minus 7 over x minus 3. So y is equal to 3 times 1 minus 7 over 1 minus 3. You can see we get negative 4 over negative 2, which is equal to 2, and that is what our output should be. So we know it's good. All right, and one more here. It says write the function y equals negative 2x plus 3 over x minus 1 in the form a over x minus 1 plus k. Remember, so we're going to refer to this one as polynomial form. It's an n, no, well, I can't do that. This is polynomial form. And this is our graphing, or you could call it general form too. And then it says to graph the function, write the equations of any asymptotes. All right, so we'll do it here. We've got y equals negative 2, and we're going to put that x in parentheses, plus 3, all over x minus 1. Now as we go to make them appear the same, we've got negative 2. We're going to add that minus 1 in the parentheses. And then we got that plus 3. That's over x minus 1. Okay, so remember, when we put this in here, we're going to have to do something over here to keep it balanced. So think about what do we have to do. Well, we'd have to distribute this negative 2 through. So when I do negative 2 times negative 1, I'm actually adding 2, right? So I'm adding 2, which means over here I got to take away 2 or subtract 2. So we're going to do minus 2 right there, right? So that balances it out. By putting minus 1 in there, it's like adding 2 on the outside. I'm sorry, adding 2 on the left side and then subtracting 2 on the right side. So what do we now have? We've got negative 2 times the quantity of x minus 1. And then when I do 3 minus 2, I get 1. So that would be like plus 1. And let's just give them each their own denominator now. And looks like we can take it and cancel these ones out. So what we have here is negative 2 plus the quantity of, 1 over the quantity of x minus 1. If you want to rewrite it, the other order. That sometimes is helpful. So our locator point, it looks like it's going to be at the point 1, -2. That's where our asymptotes are going to cross. And it's just got standard growth. Let's go ahead and graph it. So remember, our locator point's at 1, -2. So we'll go over to 1, down 2. Here is where the asymptotes are going to cross. Okay, so let's just go ahead and write those asymptotes here, right? So we have a horizontal asymptote at -2. So we're going to say y is equal to -2. Right, remember that comes from our k value up here. And then our horizontal asymptote, our vertical asymptote is going to be at x equals 1. And you can see that comes from our h value. Let's go ahead and just draw in over 1, up 1, back 1, down 1 there, and we'll just sketch it in. Should get right along there. Make sure you don't cross that asymptote. That drives me crazy. Okay, so just take your time. It doesn't have to be perfect, but let's at least not cross the asymptotes. All right, so that should hopefully help you. This is section 5.2, and we're looking at transforming our rational functions. Thanks for watching.